And we move now to the next presentation, which will be given by Marta Vanin, who holds a Bachelor of Science in Civil and Environmental Engineering from the University of Trieste, and a Master of Science in Energy Engineering from the University of Trento and the Free University of Bozen in Italy. Currently, she's working towards a PhD at the KU Leuven in Belgium and also at Energyville. And she works in the field of decision support for grid operators. Her main interests are in the analysis and operation of low voltage networks with high distributed energy resources and electric vehicle penetration and distribution system state estimation. She will present the comparison of linear and conic power flow formulations for unbalanced low voltage network optimization. And I would like to ask the host to put on the presentation. Thank you.
Good morning, I'm Marta Vanin, and I will present a comparison of linear and conic power flow formulations for unbalanced low voltage network optimization. A bit of background: low voltage distribution networks have typically been operated with a fit and forget approach, but now are facing drastic changes due to the installation of electric vehicles, distributed energy resources, and heat pumps. These technologies can cause power quality issues, but also potentially allow for valuable control actions, so there's renewed interest in analyzing these networks. However, they present additional challenges with respect to the transmission system, for example, as they have non-negligible degrees of voltage and current unbalance, high Rx ratio, radial topology, and there are many feeders of this kind on a national level. So the large-scale analysis of these types of networks is computationally intensive. So one interesting issue is to find a compromise between accuracy and computational effort. And for this purpose, this paper analyzes two simplified formulations of the power flow equations for a set of power flow and OPF problems, where we want to assess whether the formulations are accurate enough, and the trade-off between their accuracy and computational effort is interesting. The most common off-the-shelf academically available optimization solvers are tested for each problem to find the best match between a problem and a solver. The problem types are power flow with objective, continuous variable OPF, and mixed integer OPF. The addition of an objective to the power flow problem is a trick to allow to solve it with the second order con formulation. The objective consists of minimizing the power injections from the transformer substation, and this prevents the conic formulations from creating non-existing power losses, which would then result in wrong calculations. In the power flow problem, voltage magnitude and angle are fixed at the substation, which is modeled as a slack bus, and all grid constraints are included in all four problems. In the power flow, demand and generation are not controllable, and they are not in the power flow with objective problem either, but PV generation is introduced as a variable, although later assigned a fixed value, in order to include it in the objective of minimizing the generation cost at the substation. The continuous OPF consists of, on the other hand, really sees the power injections from the PV panels as a variable, and they're dispatchable, they're not fixed, and upper and lower bounds are added to all variables. Finally, in the mixed integer OPF is an example of demand management routine for congested feeders, where a binary variable is associated to a number of users and determines whether the users are required to reduce their power or not. The objective here is to maximize the user comfort while respecting all grid constraints. I don't have the time now to go through the details of this problem, but you can either see them in the paper or we can discuss them later. The chosen formulations are a full nonlinear non-convex AC formulations used as benchmark for the two simplified ones, a second order cone relaxations, and a linear approximation, which is called SDF throughout the slides. Both the SDF and SOC are derived from the same branch flow as semi-definite positive model, and they're chosen because branch flow presents numerical advantages over bus injection models, especially in the radial three-phase case, and of the various linearizations available in the literature, the SDF still includes resistive losses, reactive power, and voltage sags. So it is rather, the number of approximation assumptions is limited. Finally, all these formulations were available on Power Models distribution, which allows a common coherent implementation structure, which allows for consistent benchmarking and splitting model and solver. As you can see from the table, all the formulations are explored with all problems, apart from the second order cone in the power flow case, which can't be applied. I also don't really have the time to go through the details of the formulations, but this is the SDP from which the second order cone and SDF stem from. The SDP is obtained by dropping the rank 1 constraint on this matrix, and then this matrix is relaxed to second order cone constraints to obtain the SOC formulations, while the SDF approximation relies on the two following assumptions, namely that the line losses are much lower than the apparent power flows through the branches, and the voltages are nearly balanced. All the branch flow models rely on lifted variable space, indicated here. The contribution of this paper is the empirical accuracy analysis of the described formulations. This type of analysis is typically bottlenecked by the lack of available test cases, and sometimes the existing test cases fail to represent real-life conditions. What we do is we test the formulations on hundreds of real-life and power profiles made available by the Flemish DSO Fluvius for different OPF problems, and with an eye on how the voltage imbalance and number of buses of the feeders influence the results. I am about to show the plots with the results, so this is how to interpret them. On the x-axis, you will see either the number of buses of each feeder or the voltage imbalance level, and on the y-axis, the voltage accuracy or optimality gap or computational time will be displayed. In the plots, the results are shown for 500 feeders. Each point represents a feeder, and trend lines are reported to help visualization and to help draw general conclusions. To the current power demand made available by the DSO, we added a fleet of charging electric vehicles that makes it more interesting as it increases unbalance and recreates a potential future scenario. This is the results on the voltage accuracy for the power flow plus objective problem. The solid lines represent the average and maximum accuracy error for the SDF formulation, and the dashed lines for the second order cone formulations. It is immediate to see that the SDF is more accurate, and indeed with higher unbalance you have higher accuracy losses. However, both formulations are very accurate as the errors are always below 0,006 per unit. In the OPF case, the results are even a bit better, but they're virtually the same as the power flow case. So yeah, they're absolutely comparable. As far as the computational effort is concerned, this plot shows the computational time for the best matched solver, which is Mosaic for the second order cone, Gurobi for the linear problem, and IP Opt for the AC. And we can see that the second order cone and the AC formulations are affected by the number of buses in the feeders, while less so for the linear case, which scales much better and always solves in less than 8 milliseconds, making it on average 22 times faster than the second order cone and 5 times faster than the AC formulation. In the case of the OPF, the computational time for the second order cone formulation decreases rather significantly, and this is probably to attribute to the presence of bounds on all variables that restricts the feasible space. While for the SDF, the performance worsens a bit, but it is in average still 4 times faster than the AC and 14 times faster than the SOC formulation. For the OPF problems, we can also have a look at the optimality gap. It can be observed that, again, increasing unbalance causes lower accuracy. And the results on the optimality gap are less remarkable than those on voltage bus accuracy, which makes it more questionable whether these two formulations are suitable for applications where finding the objective value as accurately as possible is the key. So, and again, the second order cone performs worse than the SDF formulation. I'll finally go through the results for the mixed integer OPF. These results refer to a set of 100 congested feeders. So of the original 500 feeders, a subset of 100 are pushed to congestion so that a demand side management is needed to keep the grid limits in force. The results below refer to 24 time steps, which is 6 hours. Normally the complete problem we are interested in is on 24 hours, but the mixed integer nonlinear problem formulations can't solve such a complex problem. So even with only 24 time steps, it often exceeds the 1 hour time limit before it finds a solution. And when it finds a solution, it is typically around 3 to 4 orders of magnitude slower than the mixed integer linear case. Interestingly, the mixed integer linear case returns AC feasible solutions if the limits on the voltage and the current are a bit tighter than in the original AC problem, while the second order cone mixed integer problem does not in general return AC feasible solutions. The solver used for the MINLP problem is Juniper, while for the other two cases, Gurobi proved to be the most efficient. This last picture refers to an analysis performed on the whole 24 hours, and we can observe that apart from a few cases, the SDF finds a solution in less than 1 minute, and it largely outperforms the second order cone, as it is on average 30 times faster. So in conclusion, the computational time does in general increase with the number of buses, especially for the AC and second order cone problems, while the SDF scales very well. Higher unbalance does imply lower accuracy as expected. However, voltage accuracy is remarkable for all problems in both second order cone and SDF formulation, particularly the latter. On the other hand, the optimality gap results are worse, so it is more questionable whether these two formulations are suitable. It depends on the application. Finally, the SDF is the only viable option for the mixed integer problems, and therefore, as a conclusion, in all cases, the second order cone is less interesting than the SDF because it has lower accuracy and higher computational effort. These are the references I referred to in the slides, and now I would like to thank you and welcome any of your questions.
Okay, in the meantime, we have a number of questions being asked. Okay, things are moving here. So the first question is from Dan, who is not in the Q&A panel as he's one of the panelists. So for the SOC relaxation, you minimize the power losses, which is a reasonable approach. There is some evidence in other settings that minimizing total reactive power generation or other objectives can also be effective. Have you considered using other objective functions? And it would be interesting if alternative objectives fail to work well in your setting.
So no, I haven't tried any other objective function. And indeed, it would be interesting to try other approaches. I was a bit disappointed with the secondary cone formulation after this analysis. So I didn't really dive into other types of analysis and using it, okay. But it is indeed a good remark.
So we have quite a few questions. So if you are short on answer is good. Otherwise, we'll have to answer them via the Q&A. Carlton asks, your results appear to suggest that SDF is sufficiently accurate distribution level OPF in practical applications. Is that your assessment as well?
Yes, that's my impression.
Okay, good, very good and a quick answer. From Rahul, thanks for the nice presentation. In the paper, the author presented the comparison of different methods based on voltage accuracy. A linear approximation tend to perform worse in terms of current accuracies. So can the author please comment whether it reflects similar trend for current accuracies?
I haven't looked into the current accuracy for this, in this paper. For the continuous variable problems, I did during some other works, I had a look at the results of the mixed integer, and actually in the mixed integer problem, the current values are actually pretty accurate, I would say.
Okay.
Yeah.
Okay, if needed, answer more in the Q&A. We have a question for Patrick Panciatici. How do you add the constraints in a DC approximation? How did you do that?
In a DC, but it's not DC.
So you probably linearized approach is the SDF.
Yeah, so there was a slide where you could see how the power flow equations look like.
Okay, I'll provide you with Patrick's email address so that you can answer him directly. We have 2 more minutes and we the voltage constraints. I'm sorry, Patrick asked for the voltage constraints. He has an additional question a little bit lower in the slide. So the voltage constraints in the DC approximation, but it is not necessarily a DC power flow, correct? I'm answering because I'm one of the authors of the paper as well.
No, you talked too fast, sorry.
Patrick is... we'll answer Patrick separately. Maybe that's easier.
Yeah, maybe.
The question from Jiabin is, can you talk about about some details about your tested network? Are they standard IEEE test feeders? If so, have you compared your results with other calculation software such as OpenDSS?
No, so the AC formulation from power models distribution is benchmarked against OpenDSS. And while the test feeders I've used are from the Belgian DSO and exclusively from the Belgian DSO, they look like the European low voltage test feeder, if you know that one, more or less. But yeah.
The question from Line is, will they be made public? Is probably no.
No. No, but yeah. Yeah, in the meantime, I think there are some low voltage libraries from the UK that have been released. So this work is relatively, well, it started more than 1 year ago. In the meantime, there are more data sets that are available for low voltage networks. So indeed, in the future, we might want to use those instead of the DSO's feeders, because they're never going to be made public.
Yeah, that's probably a fair assessment. Okay, thank you, Marta. I think this is all we have time for, but feel free to answer some of the questions in the Q&A window yourself by typing the answers.